So welcome to the youth session, so the University School for Advanced Studies. I'm really happy to have you all, and we will wait just 1 or 2 minutes, waiting if someone is going to join, because other seminars are still ongoing, but we can start to a little bit introduce what we are going to talk about. So based on the different topics that are dealing with artificial intelligence, let's say machine learning, neural networks, deep learning, with the youth, we have been discussing about how to put on the table and to present the several different opportunities that using and combining artificial intelligence and data analytics, especially related to new imaging techniques that are applicable to health, environment, medicine, seismic engineer, and all this type of analysis within a context of what we have called since a few years the new space economy. So let's try to a little bit introduce what we have in mind in terms of presenting the different applications that are ongoing, not only at use. We have invited also external experts. So I want to first thank Giovanni Silos Labini from Small and Medium Space Enterprise Association, and all the colleagues of the University School of Advanced Studies presenting the different research we are dealing with artificial intelligence, neural network, and deep learning. So the idea is to show how we go from, let's say, data analysis to really industrial application and user application. So the first point is like how we use all these data analytics and data implementation to get to really operational system, both in application for human, but also application for monitoring environment, but not only environment. So before giving the floor to the presentation, let's wait 1 minute. And I would like to present all the different panelists. So at the beginning, we will start with a presentation from me and two PhD and postdoc, that is Maria Jose Jimenez and Bruna Alves. And we will talk about how to use Earth observation for environmental monitoring. Then I will give the floor to Giovanni Silos Labini, that is the director, of the Planetech space industry. Then I will leave the floor to the Professor Dennis Tsarigiannis, that he will talk about deep learning neural networks applied to health science. Then I will give the floor to the Professor Roberto Nascimbene, that will talk about how it can be used data analytics in seismic risk assessment. Then Professor Stefano Cappa, that will talk about machine learning and still the health. And then finally, but last but not least, to Dr. Christian Salvatore, that will make an example of clear application of artificial intelligence applied to image analysis. So I think that we have already wait for another minute, so I would like to start, and I thank Maria Jose to start the presentation. So we're going to talk very briefly to what is the Earth observation technologies for industry applications. So how can we start from a really new change of paradigm That is the investment of scientific challenges and technological development, but with a very different paradigm. So not develop technology push application, but really starting from user requirements in order to produce what is a user needs, a real downstreaming services based on what user needs are defined, and then developing the upstream parts of the development of the new satellites in terms of like new services. So in Italy, we have built quite a lot around this main concept, really linked to what is under development at European level. So the Copernicus, where European national institution, research institute, and the industry are really looking to producing a new paradigm in public-private partnership. So developing really downstreaming related to also the upstream part, but with an end user related starting point. Please, Maria Jose. So what we have called the national space economy is quite a big investment in order to have a market upstream market uptake of new services based on what we have called the mirror Copernicus approach. So asking to the end user what they need, trying to figure out what is the services based on the user needs. So asking for a gap analysis and then developing all the technology development that are behind that. Please, Maria Jose. So the major point of this approach is making a service-oriented demand linked to what the European member states are obliged to legal obligation. So making a clear analysis of which are the Copernicus application domain and which are the thematic area, so like the one related to agricultural food security, ecosystem, inland and coastal water, and we will see that there are many more, like natural hazard and man-made hazard. Figuring out which are the needs that the public institution, but not only the public institution, but also the private sector has to be stick to related to the Copernicus domain and to the thematic area. So which are the needs that has to be implemented and what is the value added that the Earth observation can bring to that domain. Please, Maria Jose. So considering that Copernicus is built on three main legs, one is the space segment, so satellite, but also in situ data, so the data delivered that are used to produce the main Copernicus services. The mirror Copernicus is making the link to produce the Copernicus economy, so the user uptake based on user needs that are going to be delivered just using not a technology push, but user-driven approach. So building on user requirements to bring operational services that can be run by the industry. Of course, the industry is one of the core business. Please, Maria Jose, and then we will make a specific presentation. I will leave the floor to Maria Jose. What are the base of the Earth observation system? So you have all the data inputs that has to be based on what is the user requirements. Then you use data analytics and machine learning to produce what we call the downstreaming services. So the radical innovation of geospatial service and how we use that. And then we need, of course, what we call the cloud computing, so the software and product development in order to have and to find the final information, not any longer data and services, but the final information that the real end user usually needs to make decision on to make acquisition and so on. So I leave the floor to Maria Jose and to Bruna to make these two simple examples that we are implementing right now. Please, Maria Jose.
Thank you. Well, there are several types of radical innovation happening right now within geospatial services, and we're going to talk about some of these examples. In my case, well, here you can see how precision agriculture and crop monitoring, terrain displacement, flood mapping, but also related to coastal hazards, climate change projections and weather nowcasting, but also healthcare monitoring of diseases, as we've seen in the in the last years that there has been a lot of innovation in this field, and there are new businesses happening related to business model based on satellite data. I'm going to be speaking about the case of Noctua. Noctua is a pilot project of a commercial service for the collection, processing, analysis, and distribution of radar satellite data for the Lombardy region. And the services, they seek to monitor infrastructure, mountain slope, and all type of natural resources using this very innovative STAR technology, which is radar technology, and it is able. One of the big improvements of this type of technology is that it can be used in all weather conditions, and it provides a very high spatial resolution. So the modeling of very realistic scenarios can happen. I'm going to talk about further on the partnership that was created for Noctua. But in the meantime, I'm just going to mention the project partners, which are the Orbit, Use, Altamira, MetaSensing, UCenter, and Beta Otanta Group. So as we've seen, we called for Noctua Map Lombardy as the services that will be provided within the project, where user requirements were analyzed first to be able to select the proper data sources, in this case, the optical and radar data from the German and Italian Space Agency, as well as the Copernicus land monitoring service was used in combination with weather information and piezometric data to provide these three types of downstream services, which are terrain displacements or ground monitoring, the crop monitoring, and the flood mapping or flood monitoring service. These services then respond to different users, which are, for example, for the agricultural industries, but also for insurance and their reinsurance companies. Since there is an emergency management type of component, we also have civil protection and regional and environmental agencies that are also interested. So this will keep on feeding this type of cycle for further improvement. So we see first that this project foresees two types of innovation. First, in the transformation of the space sector, because it seeks to integrate it into society and economy, when normally the space sector investment came only from the public sector. In the case of Noctua, we have the private sector with the Orbit, which is creating and launching this mini satellite. Then MetaSensing, that it's a private industry that also constructs this radar sensor. And Altamira does the application for the data processing, which is also a private industry. But then we have UCenter and Use that are in charge of creating the service. And here we see that we have the public sector and the research centers. And finally, Beta Otanta is from the private sector that creates a web platform that offers service that are then displayed for the final users. Another type of innovation is that it's user-oriented. So for the monitoring of the terrain displacement for phenomena such as land subsidence or landslides in urban areas, but also for the agricultural domain, where we are able to estimate the crop needs, also provide crop classification and determine the different stages of growth of a plant. And finally, for the emergency management component, the service is flood mapping that will provide fast estimates of the damage produced by floods. Now I leave the floor to Bruna, that will speak about another project.
Thank you, Maria Jose. I think you carry on with the presentation from, right?
Yes.
I cannot see it.
I am sharing the screen. One moment.
Okay. I think I can. Yeah, I can see it.
I'm sorry, I'm going to give the presentation rights to Maria because they've removed.
Okay, okay. Otherwise, I can just carry on with the speech and then.
Yeah, if just carry on. I think Maria should be able to. There you go.
Okay, now I can see it. Yeah, thank you. Thank you. Okay. So I'll speak briefly about ECFAS. So ECFAS is a proof of concept for the implementation of a European coastal flood awareness system. It is a European Commission funded project into the Horizon 2020 program. Our partnership is among institutions from Italy, like EUS, CFR, France, Mercator, and CLS, and Greece, Plantec Hellas, University of Aegean, Spain, University of Valencia, and the European organization whose name is Euroocean. Next, please. So our main objective is to develop this proof of concept that will serve as a coastal early warning system. The main data set that will be used is based on remote sensing data and also in situ data, like coastal video monitoring and several geographical layers such as land cover, land use, settlements, infrastructures, roads, and also topographic data. Those input data or these data sets interacting with the user requirements give the flow into the downstream services, which are customized services that ECFAS will deliver. They are the early warning system, mapping services, risk impact and exposure assessment, total water level forecast, and a cloud-based system called data and information access services that will make easier for the end user to access Copernicus data. Our end users are from several sectors, for example, from the academic sector, national, regional, and local authorities, civil and environmental protection agencies, private companies, European agencies, and so on. So the one before. So yeah, so their requirements are very important into keeping this cycle alive in a way that the products into the downstream services or the products cycle is carried on. Okay, so I will speak a little bit about the end user engagement approach that we are taking into account here in ECFAS. So the end user engagement is both a downstream approach and a bottom-up strategy, meaning that the users help framing project activities and also they orient the development of the final products, the downstream services. So those products and those services are more informative, relevant, and customized. In ECFAS, this approach connects the needs and requirements to the final products that will be eventually delivered by the coastal flood awareness system. We see this as a mutually beneficial collaboration between ECFAS and the end user into the co-design, co-development, and co-evaluation of this proof of concept that will be in the end integrated into the Copernicus Emergency Management Service. In ECFAS, we are carrying out a quite effective and clear strategy engaging the end user, and I can summarize here into a few steps. We started identifying the key facilitators, such as project partners, cooperative services exploitation team, and so on. The project partners are quite important here because they see the potential end users, and they go and try to engage them in the first step. Then also several activities such as webinars and even the social media play an important role here, because those channels they foster new end users. In ACFAS, we are working now with a web-based questionnaire. It has been designed with the idea of gathering information about the end users fostered in steps 2 and 3. Information about career experience, and most importantly, the end user needs and requirements in terms of operational and services. Reminders, I work pretty much with reminders with the user pool, sending them messages and encouraging those that haven't yet answered the questionnaire. So to please do that. And the message is to give it the idea that this is a real mutually beneficial engagement process. We are now walking to the direction of having all the data all together. And we hope then to start with a stat analysis, trying to find any trends in the information that we gathered from the questionnaire, and trying to find any correlation between informations. And all the results will feed all the technical work package, so the leaders can adapt the proof of concept and into the co-design of this platform, into the service being more operational and customized into the end users' needs and requirements. And I will ask Andrea to wrap up the presentation now.
Thanks. So I just conclude very briefly. So the take-home message, and this is an example, but this is going to be, the roadmap and the line of the, of this thematic session is the importance of really put the user at the center. So these two examples are, a practical example of research in that line, and concluding in making, a statement that it's of primary importance, the interaction between research and the academia with the industry, because we really have to transfer all this paradigm or research paradigm to the industry to produce a real market for downstreaming services. So I'm happy to conclude that and to leave already the floor to Giovanni, because I think it will be not only in line, but he will be way much more on the top of that, of this presentation, and also all the future speakers. So Giovanni, the floor is yours.
Thank you. I need the control. I know. Don't have yet it. Can you see my screen?
Yes,
Hello?
Giovanni. Yep.
Okay, thank you very much. So first of all, thank you very much for the opportunity to present within a university environment our activities, and just 2 words about Planetech Italia. We are about 100 people between Planetech Italia and Planetech Hellas, and we provide Earth observation services since about 30 years. So we are dinosaurs in this area, but we try to keep us updated with what's happening. I have to correct Professor Taramelli about the definition of IPAS. Is not only an association of small medium enterprise. We have a large number of small medium enterprise active in space, but also of private owned large system integrator like CTEL or Expedia. I try to go into the key issues of this meeting, and looking how we can transform Earth observation data, so well described in the preceding presentation, as actionable vertical information from the user. So there is a large transition in Earth observation generation of product, and what we are doing is transform what in the past was very nice maps in numbers that can be vertically integrated within different industries. What is happening in the space is that nowadays, thanks to an inversed technical transfer from ground to space, a lot of device developed, for example, for general consumer electronics like cellular communication or electric car are being using in space. This reduces the time and the cost of building satellites. So nowadays there is a growing amount of Earth observation constellation emerging, and this permits us to work to a transition, as I told before, from Earth observation to Earth intelligence. I will try to demonstrate that this data can produce actionable information for different applications, as already told by Taramelli, like environmental, climatic, and economic financial application. One of the advantages using artificial intelligence and the big data algorithm is to have a neutral and unbiased source of information, because satellites are in some way unbiased and produce practical data, as we will see, that can be used to extract useful analytics. These data are very interesting because are linked to different assets, environmental indicators, business indicators, as we can see later, land use, land cover in different areas. The other change that is happening is that these data are available with increasing frequent time interval, and in few time we will have a real-time high resolution Earth observation data. So this data can empower gap analysis about, for example, introduction of a new infrastructure in remote areas, impact analysis to look what is the effect of a specific project in developing country where other sources are not available, and even where these sources are available can produce third-party verification of the information shared. So combining Earth observation and remote sensing, we can measure, for example, the impacts on insurance of climate change, support the corporation accounting and for the so-called ESG, so the environment and social governance of the companies. International financial institutions can monitor and evaluate investment impact in remote area, and we can have an evaluation in short time and the long range for several communities that go from food to oil and so on. The first example I want to give you is very closely related to the EFAS study that you have seen we as Planetech through our sister company Nellas contribute. For example, the sea level rise and the extreme environmental events are becoming a real threat to the insurance around the world. The big increasing in AALS, that is the average annual losses for insurance, will increase from 10 to 20 times in the very few decades. And well, several activity in modeling insurance is related to observation related to greenhouse emission, climate change, extreme weather, and all these variables can be observed from space. And for example, here is the output of a study based of Copernicus data about the evolution of unaffordability of insurance arrangement in different areas of Europe. And you can see here that in the next 40 years, a big several areas in Europe will be no more affordable from the point of view of insurance cost for coastal risk. And the situation can look even worse if you look at the evolution in the 28. But the use of Earth observation is useful also to monitor and evaluate mitigation activity. And again, mitigation activity vis-a-vis the environmental risk is one of the way by which insurance can reduce their costs. If you want a trivial example, many of you experience the use of GPS-based black box on the cars in order to reduce the cost of insurance in base of your style of driving. In this way, using Earth observation analytics is possible to estimate, for example, if in some area some mitigation activity exists, and also evaluate the evolution of this kind of infrastructure during the time. Another application is for Earth observation is the estimation of some economic indicators. Here is the output of a study we are doing for Asian Development Bank about the evolution, about the impact of large bazaar in several area of Central Asia. This is an impronounceable market in Barakolka that show the different land cover. So the land cover that is an observable from satellite, and land cover and land use is nowadays easily extracted using artificial intelligence technology, is really a proxy of trade activity. So we use artificial intelligence to find a proper correlation between the characteristic of land cover and queues in the area of this large bazaar using very high resolution imaging. And this way we can correlate the land use land cover change with some of economic indicators. Here you see what is the product of an automatic classification on this area, and using deep learning technology, we can build a nonlinear data model that can be inverted and then use Earth observation indicators to predict economy indicators. So, for example, GDP variation will be estimated from Earth observation data classification. There is another consideration that is very interesting. While the market for the traditional Earth observation service, that I have to say is still about 80% of Planet Equitalia business, is growing at a pace of 10% year over year. This analytics from satellite is growing very much more faster. Nowadays is more or less 1 billion euro at a global scale, but is growing at with a pace of 30% following the study of North Star Research, that is a market research society specialized in this. So we expect that data analytics via satellite will generate about 17.7 billion in 2028. That is a very huge amount of money if you think that can be delivered also in a quite automatic way everywhere, every time. So, and I rapidly conclude my presentation. In this way, we believe that Earth observation analytics can support financial markets disclosure about climate risk and sustainability related analysis. In some way can be used also for verification of these indicators that are becoming very close to what is called, as I told before, environmental governance, will be used on the other side from government and the regulator for accurately assess environmental societal systemic risk. And policymakers will be able to track progress against, for example, the Paris Agreement, linking Earth observation data together with other data, obviously, to, for example, the progress on SDG. Last but not least, and this is a very good opportunity for all of us, a huge market is opening for this kind of analytics. Thanks a lot for your attention. I take a few seconds to invite any of your students or people that are following this seminar that is interested to contact me or Planetech, because we are in the middle of a huge investment in human resource, and we are looking for specialists in data science and artificial intelligence for develop this ambitious program. Thank you very much.
Thanks, Giovanni, because I think that as an expert, you know, having the point of view of the private industry, it's one of the major issues that you know, it's good to bring in the discussion. So now I leave the floor to Professor Dennis Arigiannis, that we will talk about you know, health and artificial intelligence. Dennis, the floor is yours. Not sure if you have activated the microphone, Dennis, because I cannot hear you.
Do you see my screen, Andrea?
I can see white. I think you're sharing something, but it's for me it's white.
It is very white, yeah.
Yeah.
Give me 1 sec.
Yeah. Now it's popping up.
All right. So we're talking about I think something that is really a very important topic for the future, and that is how environment and health, how we need to understand better the interaction between environment and health, especially after having gone through the current pandemic, because there are very clear links between what's happening now and the infectious disease based health risk, global health risk, and the environmental condition in general. So we're now talking about the planetary interactome, if you like. So the interactome is a term that has been coined to address the interactions, especially mostly within the human body, mostly between proteins and among proteins, essentially, because this is really a very complex and big data-based kind of system. But indeed, we're talking about in the planetary interactome and the trying to identify the links between climate, environment, the societal dynamics, and public health. And so, as you see, sorry, as you see, there are very important links amongst them. Climate change, of course, has links to social impact, both with regard to the primary, secondary, and tertiary sector, affecting issues like livestock and harvest production, and that's, of course, affecting food security globally, but also the security of livelihood, the possibility of people to conduct satisfying lives, and at the same time, it also affects poverty and indeed human behavior. So this, of course, has links to demographic shifts, to production shifts, even on a global scale. So sort of moving around essentially the globe, and thus it affects also the overall transmission, but also emergence of pathogens, by also affecting the availability of hosts to carry them over. And we're talking about different types of infectious disease: vector-borne, waterborne, foodborne, airborne, and also, of course, also other types of infections. All of these are, of course, affected by climate change and the differentiation that this brings about with regard to precipitation rates, wind patterns, humidity, temperature, dust concentration, and even other types of issues related to the changing of climate. You realize that if we really want to tackle this complex super system, if you like, on a planetary scale, this becomes very fast a very difficult to tackle problem. Sorry for the cough. But indeed, now with the big data capabilities that we have available, this is now becoming much more doable. So in this in this regard, we definitely all consider that we need to go for a paradigm shift in terms of understanding how future threats coming from the environment on human health would actually appear. So here, this is a line of thinking in terms of needs identified in I think a keynote publication we have co-authored with a very large group of scientists across Europe, talking about the emergence, spread, and health impact, and the social response, and also eventually the socioeconomic recovery plan from infectious disease like COVID-19, and the actual need for multidisciplinary research for transformative action, which means, again, the need for tackling big data becomes very important. So I'm going to show you some very key examples of these. What happened with regard to, for instance, the interactions between COVID-19 and environmental pollution-related disease. This is an example of what we call a high-dimension biological analysis, including different types of omics technologies, looking at how the metabolome, so the whole metabolic profile of individuals changes from both the disease, I mean the virus itself, but also looking at how other interactions in prior disease actually interact with the chances of having a perturbed immunological response. As you see, we're talking about indeed very large data set, which required essentially what I might call a data-driven approach to be deciphered, because it would be impossible to create, let's say, an overall theory of how all these different mechanisms interact with each other. So as you see, we have indeed seen that there's a major immunological shift between mild and moderate infection, and indeed that you have a significant drop in blood nutrients in the case of severe disease, which is related to significant inflammation. So here, keep this in your mind, because we're going to talk also about how COVID-19 interacts with air pollution now. So as we all know by now, the dispersion of SARS-CoV-2 has the aerogenic road, the aerogenic pathway, so the air pathway as the secondary most important route. And indeed, we all already know through epidemiological studies that the prior exposure to fine particles actually renders people much more vulnerable to severe COVID-19. And thus increases mortality from the disease. Now, what is interesting is to be able to understand why this happens and how this links to issues like, for instance, mitigation or adaptation to climate change. And here you see how, for instance, mitigating CO2 emissions can result in increased air pollution by extended use of biomass, by use of diesel in the case where diesel has better diesel engines may have better features in terms of CO2 emissions than gasoline. And also, and even more importantly now with COVID-19, the increased building insulation, which obviously is a very good solution for energy efficiency, at the same time may result, if we're not careful, in increased indoor air pollution and also eventually increased possibility of transmission because of not enough ventilation of infectious disease like COVID-19, but also other types of infectious disease, including the flu, including MERS and SARS, and also even tuberculosis. I mean, it has to do with where you're actually putting the overall radar of disease that you want to tackle. But it does show how, indeed, solutions that may go in the right direction in one dimension, say climate change, because you save on energy, may actually be problematic in another dimension, for instance, the question of infectious disease. That's why we're talking about building a risk emergency toolbox in the case of facing, for instance, COVID. And here what we have been designing with a group of another consortium of European partners is indeed a setup where advanced environmental sensors and even biological sensors like on-site DNA sequencers can actually be linked to telemedicine information, as you see here. And all of these get used, become input to a big data analytics platform, which actually allows to understand, manage, and explore the relationship between these data sets to then be fed into a model of the disease or the pandemic, which allows us then to estimate properly, this is the model I was talking about, to estimate properly the dynamics of the disease. And this model even, which as you see, takes into account a number of issues, including risk management measures like masks and distancing, social distancing, or even disinfection systems in indoor air, also has to take into account social behavior. And in order to do that, you need to actually use AI techniques, artificial intelligence techniques, and big data analytics, because we need to actually, as we all know, we don't do the same thing, all of us, not everybody behaves in the same way. So we actually use, in this case, agent-based models to try to simulate what the human population would do in the sense of applying and implementing the actual risk management measures that have been over time been proposed by different governments. That is very important because it allows us to then have very good and precise estimation of the transmission and the progress of the disease. As in this case, this is the sort of graphical representation of this modeling scheme. And that is the kind of results we are applying this right now as an official modeling scheme for, in the case of Greece. It has equally very good results in Italy, but these are the latest results from Greece. As you see, we can actually estimate pretty well the actual all the different waves from the beginning until today, in terms of incidence, in terms of hospitalizations, in terms of needs for intensive care units, and eventually, unfortunately, also in terms of fatalities. So all the basic indices that are important to be able to capture the dynamics of this kind of problem. what I'm trying to say is that what is important is to be able to embrace the connectivity, the complexity, and of course the connectivity among different systems. In this case, and actually find the solutions that relate to this, that take stock of this connectivity. And here, the suggestion is to use. The suggestion is to use ecological health observatories and living labs. To be able to respond to an increasing demand of society for sustainable management of ecosystems, and here by sustainable I also mean safe, so with regard to safety. So the connectivity approach requires bringing together, as you see, a whole horde of environmental data, a whole horde of biological data. You can see the large data sets included, and also actually clinical data to be able to corroborate what's happening with regard to the links between environment and health. And by building these ecological health observatories and the living labs, so including the ecosystem together with health in one health approach, and also the society as part of science, as essentially citizens as part of active researchers in a living lab concept, allows us to hopefully to be able to tackle this, but also future threats which may be similar to COVID-19, but actually may also have other types of roots, for instance, climate change or other issues. This goes in line with WHO recommendations and also OECD recommendations, and I think this is very important for the future. And what is very important is to identify the fact that the cost of the response to threats like global threats, like in this case COVID-19, we are already estimated to be significantly higher than the cost of prevention. So it is in prevention that we need to invest, and not only in risk mitigation in this sense. So there's a number of research needs that we need to consider. And one thing I'd like to say here, and this is where big data analytics and big data science becomes really very important, is that this research needs to be consequential. So it has to have consequences, and it has to be solution oriented, not just research for research purpose. But it has to be able to embrace the complexity of the issues addressed and focus on the most vulnerable parts of the system, and indeed be able to relate to proportionate responses to the scale of the threat using the best available science, and also allowing us to communicate as clearly and consistently as possible. I think this is very important because we need to find solutions and address these issues together with the people, together with society, and not just by having science providing the tools and then society applying them. It has really to be a unified approach that actually brings the scientific research and the technical tools in the hands of citizens, and actually allows the citizens to become part of the scientific team as such. I would close with that in the case, in the interest of time, and of course I'm very open for questions. Thank you.
Thanks, Dennis. So I'm happy to tell that it's quite evident how the different thematic area can really make use of this new way of doing research. So in order to speed up and then maybe having a final short roundtable, I will change completely the thematic area, and I leave the floor to Professor Nashin Bennett, that will share with us, the seismic risk assessment, using the new era of data analytics and so on. So please, Roberto, the floor is yours.
Thank you, Andrea. I am okay. I can see now, and I can share my screen. I think you can see my first slide. Then I on the full screen view. Let me start immediately by skipping the first title of the presentation and going immediately to the second slide, because during this talk I would like to show my oh, it works.
Yes, I can see a presentation.
Okay, because okay, I don't see my presentation now, but let me. I don't know why. So the presentation. Let me try to share the screen and share it again. Okay. Right. Let me. Oh my God. Okay. Now you see it. Yeah. Okay. Let me. Okay. I was here saying that my idea is to talk to you by trying to explain what is our activity in seismic risk assessment and why big data and data analysis is so important in seismic risk assessment. So you know that seismic risk analysis wants, let's say, to the term adverse consequence that people and society might suffer as a result of future earthquake, let's say, but we can speak also of future events like extreme events, natural events, and at the same time estimating the probability of these consequences for some future time period. The three are the main fundamental parameter in seismic risk assessment: hazard, vulnerability, and exposure. Hazard, seismic hazard, is the probability that an earthquake can will occur in a given geographical area within a given window of time and with ground motion intensity exceeding, let's say, a plateau, a given threshold. Seismic vulnerability of a structure is a quantity associated with its weakness. In case of a quake of a given intensity, we know that masonry building is completely different from steel building, and exposure is the quantified potential loss from business activities after an event. Think, for example, that if we have a big pharma that stopped the production of safe life medicine for a week, but also for a few days, this is really a big issue. So we need to analyze and put in an app or in a software this kind of flow chart. Next step is let's say that we have end user that can be a large corporation, private enterprise, local government, that usually analyze their portfolio of properties, that means 100,000 of building, in order to best allocate funds, I say limited funds, for structural strengthening of building or other, let's say, risk reduction measure, such as emergency planning. And in calculating the risk, each facility in the portfolio, potential life safety and economic losses, is mainly due not only to the structural damage, but we need to think also to ancillary element, what we classically call non-structural equipment, content, business interruption, and these are really important for connecting our seismic risk analysis to the big data, because we start from one building that we move it to a portfolio of building 1,100, and for each building we collect 100 and 1,000 of data, and think that non-structural element may cap the majority of the total monetary investment in a building. Think to an hospital, for example, a strategic structure. And damage to non-structural element occur also at a very low level of the ground shaking. It could be clear from this slide that we started to collect data. Collecting data means that, for example, during our last quake in Italy, we did the inspection of 700 of building, big building, and I can spend hours showing damages to both structural and non-structural element, light and EV ceiling system, glazing, and to see if elements are displacement sensitive or acceleration sensitive. But I wanted to answer you a different question now that is more linked to the to the first presentation during this session done by Professor Taramelli is can we obtain from Earth observation technology, from information that can help us in doing vulnerability? Yes, we can. And this is a link that I'd like to investigate more in the future in our activities. On the left side of this slide, you can see a building before the event that we obtained with a very easy instrument that is Google Street View. And on the right, the photo that I did on site during during the quake in 2016. And it's very important that the general observation from the debris of the collapsed unreinforced masonry wall was that, let's say, the fire crate bricks were generally of sound condition, but that the mortar was in poor condition. That's a technical aspect that we can, that our picture, our figure can reveal us. But in most cases, for example, the fallen debris had collapsed into individual bricks rather than as larger chunks of masonry debris. And this is another good information. Where wall exhibits, like in this case, in the upper right of the slide, some damage with crack that mostly seem to pass vertically through over door windows, it can give another type of information. Our idea is to try to link this Earth observation technology with an ability of an app to produce directly a numerical model able to obtain more information on the seismic fragility function of our building. But in this presentation, I want also to tell you that we observed many damage not only in strategic building but also in industrial application, where many data are required to investigate the model. Here are some examples of industrial chemical plants that had big damage during another quake in Italy in 2012, 20th and 29th of May 2012. And exactly close to that is the numerical advanced finite element model that we did in order to better understand what happened in reality. It's important to be a part of a reconnaissance team after an earthquake in order to collect more information that can put in a database in order to simulate possible scenario for future analysis and to create a link with the advanced numerical test in order to calibrate model and simplified model for vulnerability approach. And next step on this is that, as I told you before, public and let's say private end user agency, firm, state government analyze their portfolio of structure and non-structural element for life safety and for operational limit state of their building. But not only, because there's also the interconnection of infrastructures. Interconnection of infrastructure does not mean only bridges, but also water, road, highway, electric power system are also considered. And the insurance company usually routinely, I can say, employ estimates of seismic risk in their operation, for example, to determine appropriate insurance rates, monitor over accumulation of policies in a small area, poor case insurance. And we can say that the seismic risk analysis can be often done using seismic modeling computer programs or apps, as we did, which usually use the seismic as inputs combined with many other information regarding vulnerability. And this gives us a kind of tool able to create a scenario that make us able to create a kind of prioritization in the decision regarding the possibility to invest fund on strengthening and in general emergency plan. Just to show you some big data that we collected together with EU Center, and this is the opportunity to thank the Department of Risk Analysis headed by both the EU Center. We collected data about more or less 10,000 of residential building, 50,000 of school building all over the Italian territory, over a large area of a very earthquake-prone country, hospital, strategic structure. We collected data on bridges, tunnel, airport, airborne, and industrial plant. Industrial plant is also a part of a big project that we developed together with Professor Sarigianis in the last 3 years. That is ability of industrial plant to store chemical liquid and effect on health in case of spillage of this liquid or gas. We know that big data means the creation of a database is an extremely large data set that may be analyzed numerically, computationally, to reveal a kind of patterns, let's say a trend, an association relating to human behavior, social interaction, scenario for improving emergency management, and online with these, we were able to let's say create a big data environment for real-time earthquake acquisition and visualization. We move from many input like PDF, CAD. We create a very advanced finite element model for thousands of building, doing many thousands of time history analysis and simplified approach in order to check with this data analysis the vulnerability and the priority of intervention and the emergency management. Priority, in many cases, emergency means also that we develop a kind of multi-objective route planning model that is able to give the emergency people that go there the best way, the best route to proceed in an area that has been struck by a big earthquake. It's a kind of traffic management of a disaster area after an earthquake. Here is an example of our WebGIS platform, again developed at the EU Center, that was a partner also of a project that has been described in previous presentation. The platform for the assessment of seismic risk and the creation of damage scenario in real time for structure and infrastructure. Through this platform, without any kind of particular computational skill, the user can view the exposure, as I told you before, vulnerability, hazard, risk data, risk big data, and these data are more or less available, as you can see here, in map or table with dialog box. There's many platforms of this kind. For example, this is we have a platform for infrastructure. So we have a platform for industrial plant. This is just an example of a platform for school building. That give the possibility, allow the real-time assessment of the seismic risk. We start from an exposure model. We define a fragility function for each building. Every point that you can see there is a school in our country. Then you can use a different type of conditional or unconditional analysis. You run many types of different simulation for simulation earthquake or for real earthquake in order to capture the real scenario after an event. It's really important that in this big data collection of information, we are strongly in a relation with an experimental test and laboratory, because real life is our targeting point, and we have at our disposal more or less 4 shaking table, from one uniaxial that is 6 × 5 meter that you can see on the left for very big building that we tested, till the last 2 that we call 9 degrees of freedom shaking table. I will try to show you in the next slide if they work some video of experimental tests that we did in the last year at the EU Center, where you can see some industrial application, where you can see a reinforced concrete building with masonry infill and the rocking behavior of a CERN application that we tested. But at the end, more or less at the end, just 1 minute and the last presentation, this is the last shaking table that we did. It's a dynamic interstory simulator that we did at use in the EU Center laboratory, where you have 2 shaking tables, one on the bottom and one on the top, that is able to simulate what we call interstory drift. That means what it happens when you have a floor acting on a high building, for example, and it's very important to capture the behavior of non-structural element on your building. These data can be used inside your application, inside your app, inside your software, for doing a seismic risk analysis with hybrid simulation with the test. I think this is my 15 minutes time, and again, I'm at your full disposal for the next question if they come. Also by mail, here you can find my mail. I think that Andrea, now the leading is still yours.
Thanks, Roberto. Thanks for the presentation. So I'm happy to say that you still see that different application when we are talking about like putting together data. So we go back to medicine and health, and then we leave the floor to Professor Kappa, that will talk about Alzheimer and new evolution. Please, Stefano, the floor is yours.
Thank you very much. Can you hear me?
Yes, perfectly.
Can you see the slides?
I can see the presentation, not in a full format, but once you...
Okay.
Yep, perfect.
Is it ready?
Yes.
Okay, lovely. Thank you very much. It's a pleasure to be here. I must say, I'm going to bring a sort of different point of view, because I'm clearly not an expert in artificial intelligence and data analytics, but I became sort of passionate about it for a number of reasons as a user. I gave this sort of grand title, which I copied from a meeting we had last month in Germany, because my main research and clinical interest is in neurodegenerative disorder, in particular in Alzheimer's disease. And I think Alzheimer's disease is one of the areas in which the advantages of the progress in machine learning techniques, artificial intelligence in general, and advanced data analytics is becoming more and more clear. I would say there are many reasons why Alzheimer's disease represents a sort of priority in this area. I can skip the... Okay, I'm trying to move. Okay. First of all, it's a very frequent disease. It has an increasing prevalence. I won't tell you the usual story about the aging of the population, but it's true. It's associated with really skyrocketing costs. So we are really in need for advanced solution for research. The second point is related to the research of the last, I would say, 10 years or so, or even 20 years. Now we know that the disease is characterized by a very long preclinical stage. So there is the need for efficient tools for early diagnosis from the point of view of development of therapy, which is what we really aim to, and from the point of view of prevention. The third point, which has played, is playing a crucial role from the point of view of stimulating people in looking into the power of advanced data analytics and artificial intelligence, is the increased availability of huge multimodal data sets. It's really big data, which are becoming the sort of having a primary role in this area of research, at least at the level of clinical research, because we are putting together. It's a complicated enterprise, as you know, because there are many barriers. I would say the most awful barriers are those related to data sharing problems from the point of view of privacy, etc. But there are many additional layers of complexity in this area. But still, we are becoming more and more able. And I must say, in Europe, we have some advantages from this point of view. Of clinical data, of imaging data, of omics data, which we can learn to exploit in a very advanced way to get useful information. Okay, this was a slide which I always used to indicate that neurodegenerative diseases really carry with them a huge burden. It's a sort of burden which is sometimes less apparent than the burden related to cardiovascular disease or to cancer. But from the point of view of having people who survive many years losing their autonomy, the impact is really enormous. And this is shared among two very common diseases, Alzheimer's disease and Parkinson's disease, which are clearly age-related, so increase with the aging of the population, and also with the rare disease, which, however, is really devastating, which is motor neuron disease. In this talk, of course, I'm just focusing on Alzheimer's disease. So I won't spend much time in this, but just to give you a feeling about this very important story of the long prodromal and preclinical period. This is a classic diagram which gives you an idea of what's going on. Basically, you start to complain about your memory, or other people start to complain about your memory when you are typically when you are in your 60s. Of course, this can happen earlier and later, but typically when you are in your 60s. If you have here a time scale, this is late, because the process which is responsible for the pathology that you might have, of course, having impaired memory is very common and it's part of healthy aging, but you might have the neuropathological cause of this started at least 20 years earlier by a slow process of accumulation of misfolded proteins in your brain, which precipitate in crucial areas for memory and for other cognitive function and kill neurons, to make a long and complicated story short. This was suspected, and now we know it for true because of because we have powerful imaging methods which allow us, for example, to see the proteins, the misfolded proteins, very early in the course of disease. But now we have many tools to measure the biological and imaging parameters in the very early stage of disease, or even preclinically. Preclinically, of course, is a different story, because this would require screening of the population, and for a number of reasons. Number one, that we don't have a really effective treatment. I don't think this is now the crucial point. The crucial point is making diagnosis early. That is when people start to complain, but because this is the phase in which any treatment should be tested. Because if you reason on this sequence, changes which happen for 20 years and then neurons dying, of course, if you plan to use a treatment when the neurons have died, doesn't really make very much sense. You should start earlier. So let's skip a few things. So we know that there is a long story before becoming demented, and we are really interested in these stages. And in order to measure these changes, which indicate that you are in the early phase of Alzheimer's disease, there is a whole lot of things you can do. And in this whole lot of things you can do, data analytics are now playing a major role. Everybody knows, I think, about the application of data analytics technique and machine learning and deep learning to imaging analysis. And I think that Christian Salvatore will talk about this in much more detail. I just want to point out that there is a big evolution in this field. From the early stages, by early I mean 20 years ago, because this is a recent field of applied research. The application of quantitative assessment to imaging data, which allow you, for example, to study the size of a certain crucial brain structure, such as the hippocampus, which is responsible for some aspects of memory function, those which are sensitive to aging and Alzheimer's disease. You just measure the volume, and you can decide whether this decrease of volume is pathological or not. To the application of machine learning method, I'm going very fast because this is going to be a topic further discussed, to more advanced methods based on a parcellation of the anatomical images, towards the sort of exciting field which is happening, which is radiomics. The main advantage of radiomics is that this is really big data, because you don't really need to have special acquisition, special pre-processing of the images, but you just can apply these sort of tools to really huge data sets. Okay, but what I wanted to emphasize here with you is that the application of machine learning, deep learning, and advanced data analytics is not only on the images. There is a lot of work going on clinical data, a lot of work going on clinical records, and in this area, the developments of natural language processing are playing a major role, because just think, when anybody gets in the hospital, a lot of data get collected, and then usually they lay there, written by hand, also on electronic records which nobody use. Okay, this is really a treasure of information which we are now learning, or at least beginning to learn how to take advantage of. You have neurophysiological data, you have the omics data. I mean, a lot of stuff which is quite often lying there without being put to use. I'm just showing you the two very small examples from our own work. I happen to be very much interested at the research level in language and language disorders. Okay, if you analyze linguistic production, you get huge amounts of data. really huge amounts of data because you can count poses, you can count nouns and verbs, etc. You generate huge data set to which it's quite natural to apply, for example, machine learning methods. This is what we've been doing in order, for example, to diagnose differences between patient affected by a suspected pathology and normal controls in the very early phase of disease. In this case, it's a sort of rare neurological disorder associated with language impairment. This is another example of work we are doing in collaboration with our friends in the UK, which is also very promising from the point of view of one of the application, which is basically classification, normal, pathological. An area in which I'm particularly interested, well, we are all very much interested in. This has been very much primed by the COVID situation, is a digital assessment with the possibility to apply this in a telemedicine context. There are a lot of commercial tools available or non-profit tools available. For example, this is the program developed by the NIH. This is a commercial tool. This is another commercial tool developed by Philips. This is a project in which I'm participating. This is related to the work I was mentioning on language disorder. This is an effort, well, it's already commercial actually, to develop an application to perform speech analysis and comparing the patient data with the control data. Mobile technologies. Okay, this is a very interesting story. I don't have the time to go into it, but the advantage of mobile technologies is to go towards a sort of more passive assessment that is not asking people to do things, but collecting data while people are in their real life. Very interesting, for example, from the point of view that Professor Sagliani was mentioning, that is social contact. Very easy to get information about this from mobile application. These are some initiatives we are working on at the use. One project is with the Ministry of Health, which is really first step, which is because it's a digital assessment with administration supported by tablet, and we are also working through a collaboration with a company and a group of Italian scientific societies on a remote neuropsychological assessment platform. So final slide. What we really need, however, is not only advances in these subcomponents, these imaging, clinical data, omics, etc., but put all this stuff together for a number of goals, possible goals. That is classification, stage, differential diagnosis, prediction of progression. These are all progressive disorder, and you want to be able to tell people what's going to happen in the very early stages, and much more than that, to be able to measure the possible effect of interventions by this kind of fastly developing and really exciting approaches. And I think I'm over.
Thanks, Stefano. And so before going with the final presentation of Dr. Christian Salvatore, I was wondering if there's already some questions that would like to be popped up, or we will wrap up with a sort of like a round table at the end. I'm not seeing any question right now, so it's good to leave the floor to Christian Salvatore, and he will tell us about, new perspective image analysis still in a medical prescription and health. So Christian, the floor is yours.
Thank you, Andrea. Thank you all. Okay. Can you see my screen?
Yes.
No. Okay. Okay. Thank you. So thank you for the presentation. Just to go on to the point, I am Christian Salvatore. I am a senior researcher in applied physics at USE, and I am also CEO and co-founder of Deep Trace Technologies. That is a spin-off of USE, in which we try to apply artificial intelligence to imaging and biomedical data, in particular, to perform kind of early diagnosis and prognosis, and so to try and make this sort of things that I'm going to explain in this presentation. Specifically, in this presentation, I'm going to show how artificial intelligence can be applied to biomedical data to support medical diagnosis. We all know what artificial intelligence and machine learning techniques are, and in which ways they are changing every field to which they are applied. But we can focus on medicine, on biomedical data, and specifically to medical imaging. If we focus in this field, we want to try to understand how artificial intelligence can be used to support the clinical decision. And to do this, we must understand which are the main clinical questions that are important in this sense. We can focus on diagnosis. That is the question that the clinicians make when you want to know if a patient is in a healthy condition or in pathological condition. Prognosis, that is the question of what will be the course of the disease. And then screening and treatment addressing, that are two biggest problems. But we may focus on these 2 points. So, can artificial intelligence be useful for clinical diagnosis to support diagnosis, and then for prognosis? Just to give you a practical point of view, I want to show you 2 different case studies. The first of which is the diagnosis of COVID-19 pneumonia, just to be concrete. When I say me, I mean at the research group at Deep Trace Technologies and USE Pavia, we came in contact with the problem of COVID-19 diagnosis at the very beginning of the pandemic. That is in March of the previous year, just at the beginning. So at this stage, at this phase, some hospitals from Lombardy asked us if their data could be useful, could be applied to extract information that could be in support, that could support their clinical diagnosis of COVID-19 pneumonia. Just to do this, to understand if this data could be useful, we tried to apply and to extract information from the chest X-rays of more than 600 patients, and we tried to train a model to automatically discriminate between COVID-19 patients and non-COVID-19. So this is just a representative image to see the chest of healthy and pathological patients. And what we did is to implement a deep learning model, so a convolutional neural network that was able, to be able to see which were the differences in chest and CXR images between these 2 groups. So we wanted to see if deep learning could be able to make a sort of automatic or support to the diagnosis of COVID-19 pneumonia. And after training this deep learning system on more than 600 patients, we saw that the system was effectively able to automatically diagnose this kind of disease with a very good performances. In this case, as we see here in this part of the table, with a sensitivity of 80% and a specificity of 81%. Sensitivity is the ability to, detect the pathology. Specificity is the ability to detect the healthier condition. This is are the performance on an independent testing set. So these are new patients. Once the model was trained on a given data set of patients, the model was then tested on new patients from the hospital, obtaining these performances. So these are good performances that can be effectively used in clinics. As a comparison, human independent testing, so 2 clinicians that were to which these images were given reached comparable specificity but a much lower sensitivity, so they were not so able to understand where the pathology was present. And much more important than classification, we were able to extract these sort of maps that show where the deep learning model watches, so where it was looking at which parts of the CXR it was looking at when making this diagnosis. And this is very important because it gives us a sort of performance or goodness of the algorithm in making automatic diagnosis, and also because this is the only way for a clinician to really trust an artificial intelligence method like this, because it can really understand what the machine looks at, and which is the, if we can call it like this, which is the reasoning behind that automatic classification. So further step, we understood that AI could be applied to diagnose COVID-19 pneumonia from the healthy condition. But what if we asked AI to automatically classify COVID-19 with respect to other kinds of pneumonia? So what if we asked it to perform not diagnosis but differential diagnosis? And to understand this, we extended our dataset to a dataset of more than 1,200 CXRs, so patients with their chest X-rays of these 2 groups, so COVID-19 pneumonia, healthy, non-COVID, no pneumonia, and a middle group of patients with pneumonia obtained from different ways, I mean viral or bacterial pneumonia. And these are, for example, the images of patients with COVID-19 pneumonia, viral pneumonia, and bacterial pneumonia. We asked and we trained the same model, so the same model as before, to understand if it was able to make differential diagnosis. And in fact, it was. We can focus on this part of the table with a sensitivity and the specificity over 80%. So very good results also in this case. And as you can see, in an independent testing, performances were much higher. So a result of this study was published on scientific publications, and also it was the only AI system, AI algorithm to be included in this WHO, World Health Organization, about a rapid advice guide to use chest imaging for the COVID-19 diagnosis. But so we focused and it was the first part of the presentation, we focused on diagnosis. But what if we ask AI to go beyond diagnosis? I mean, diagnosis can be performed also in the clinical practice. When we applied AI to COVID-19 pneumonia diagnosis, there were not much rapid ways to diagnose COVID as there are now. But in this case, we can call it a sort of automation of a process that can be already performed in clinics. But what if we ask it to make something that goes something beyond diagnosis, and so to perform something that clinicians cannot do? And here we can link with the presentation that Professor Kappa made just before. To understand this, we try to apply AI to the prognosis of Alzheimer's disease. Just to give you some information, as we saw before, AI, I mean, Alzheimer's disease is a neurological and neurodegenerative disease for which there is no cure. And also the diagnostic process, as we saw before, is not so simple. I mean, diagnosis to date is here. So when cognitive functions are much lower than the normal clinical and cognitive decline. What we wanted to know is if diagnosis could be made at this phase, at this point. This point is called mild cognitive impairment, and in this case there are early symptoms, but clinicians and neurologists cannot diagnose with good performance subjects with MCI who will progress to Alzheimer's disease from subjects with MCI who will remain stable, that are called stable MCI or not converted MCI. So we wanted to focus and position ourselves here in this phase, just to make early diagnosis and to predict sort of prognosis of the progression of the condition of MCI. So to see if these patients would have progressed to Alzheimer's disease dementia or not. In order to do this, we used and we collected a dataset of 200 subjects, and we followed them for 2 years. So in this case, at time 0, we collected the structural MRI. This is a magnetic resonance imaging, a widely used imaging technique in a lot of clinics, potentially and possibly coupled with neuropsychological assessment, so with the results of neuropsychological tests. We collected this data at time 0, and then we followed the patient for 2 years, 24 months, in order to see what will be the diagnosis of these patients 2 years after the data collections. So here we had MCI patients together with normal condition and AD, and at this phase we had all or stable MCI or converted MCI. We used this data at time 0 to train a model to automatically separate these patients, and the target was the diagnosis at 2 years after this data collection. So just to be clearer, we had this data set with subjects with some cognitive deficit at different level suspicious of for AD, so MCI at this phase, and we wanted to see if the machine learning AI system was able to separate this population into MCI that who will not progress to Alzheimer's disease dementia within 24 months, and MCI who will progress to AD within 24 months. And then to use this model to classify, to support the prognosis of new subjects. So we trained the model, and I'm showing here you the results. We obtained very high performance in classifying these patients. because we obtain 80% accuracy, and these are sensitivity and specificity for this method for classifying patients. So for the prognosis of Alzheimer's disease dementia in MCI subjects within 24 months, so 2 years before the stable clinical diagnosis, 80% using only magnetic resonance imaging, 85% using MRI plus neuropsychological assessment. Just by comparison, the error, the human error, the neurological clinical error in case of MCI-AD is 40% to date. And most important also in this case, we were able to extract which were the best predictors of this model. So these are the areas the AI system looks at when it is trying to classify a new patient into one of the two classes of this clinical question. And these are all areas that are known to be involved in the pathophysiological mechanisms of Alzheimer's disease, just to underline again the goodness of the model and just to make clinicians and neurologists see and trust how the system works. This is very important for the translation from research to industry. Just to going to conclude, this tool, so this research about Alzheimer's disease is now a commercial tool on-premise, both on-premise and on cloud, that has received some months ago the CM marking, and so that can be effectively used, and that is used in clinics, in some Italian clinics, and through this pattern that we workflow that we is similar to the one we saw above, the neurologist can upload to the system, in this case is the cloud system, the MRI of the single patient that he wants to classify, possibly potentially coupled with the neuropsychological tests, and in about 15 to 20 minutes he receives a report about that single subject. So it works at the single subject level. It receives a report with the risk, so low risk or high risk for that patient to develop, to progress Alzheimer's disease dementia within 24 months. And just to conclude the last slide, I want to stress some points that for me are important when implementing a new system that should be used in clinics. These are the requirements that clinicians make us when we work with them, and so clinicians want obviously to have a predictive model that achieve the best classification performance for their specific clinical question. But second, but I think at least as important as the first one, that system, that AI system, has to provide interpretable results. So results that can be shown both to the patient and to the clinician to trust how the system is working. And all these methods have to finally, in the end, to support clinical decision, and they don't have to substitute clinical decision as it works now. Just to say, we saw that AI is already in use within the healthcare systems, and some systems are already in use. I just want to stress one last thing, because there is some hype about this argument, this topic in the last years, and it is not really the case, because humans are still in the loop, and they will still be in the loop, not just because these methods have to support clinical decision and not to substitute, but also because humans, clinicians, are the only way to train AI system to work properly. So as I like to say, AI can support humans only if humans can support AI. So thank you for your attention.
Thanks. Thanks, Christian. Really interesting presentation. So we have still a few minutes, and I want to pose at least one question, more or less to all the speakers. But I take the chance to start with Christian's, because I like the point that humans are still in the loop. So you said that in this way we are always saying that when we talk about like experience in data analytics, in Earth observation, it's the point how you interpret and how much information you put on the on the image interpretation and so on. So my question to more or less of the speakers, if I see what you are doing with diagnosis, how do you think, because we are talking about like technological transfer to industry, to technological, how much exportability has your approach to very different thematic area? We have seen that within youth, but also with the intervention of Giovanni Silos Labini, the different application of data analytics can be really wide. So if I have to invest, and we're talking about like economy, new space economy, new economy, and so on, how much of your experience in human diagnosis can be exploited in a very different sector like land use, land cover, or like agriculture, like seismic? So how much of your approach can be exported to others? But the same can apply to what Professor Nascimbene was presenting, or also what Maria Jose and Bruna Alves were presenting. How much an artificial intelligence can be really applied with a similar model to very different thematic area? Christian, the first answer is from you.
Well, I think that I have to say a percentage. I think the percentage is very high because both imaging techniques and data acquisition techniques that can be used in medicine, for example, and in different fields are very similar. I think cultural heritage, for example, or I think environmental science, for example. But also AI techniques that can be used in medicine to analyze, manipulate, and then extract information and classify medical imaging can be easily translated to these other fields. So I think that the percentage is high. Obviously, it's not 100%, but we can say that at least 60 to 70% of knowledge can be shared between these disciplines. At least if we talk about information acquisition of information, so imaging techniques and AI techniques that underlie these systems. So I am positive about this point.
Thanks, Christian. I still don't see questions on the chat. So what is your point, Roberto, about that? Christian is pretty positive, and I'm positive like Christian, because I do think that there's several overlap in, let's say, image data analytics. Oh, Dennis, you're still here. I thought that you were gone. So I leave the floor to Roberto for a quick question. Then I also ask the question to Dennis, but also to Stefano. Even if you said that you are not expert about artificial intelligence, but you have seen several applications.
Andrea, I'm really optimistic in a couple of ways. First, with you using of images from spaces to study structure, that I think would be the future on this topic. But also with Christian, we already are collaborating and did some project together with Professor Sarijanis about the effect of liquid and chemical product on the health of people in industrial plant, and that could be taking care of worker in many industrial applications. I think using images and AI could be the future, and some really challenges application in big data, in data analysis. Yeah, sure.
Thanks, Roberto. Dennis?
Actually, I fully concur. I think that indeed it's a question of crossing borders and sectorial silos here. But these are enabling techniques and enabling approaches which would allow us to really collaborate across different fields. And in this sense, we really need to try to invest, if you allow me, because we are among also professors here, to invest into building lateral thinking into our students. So really make them understand how what they do relates to what others do, not what they do alone, which I think is very, 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 very important for the future. In this case, I really think the combination between advanced imaging techniques and sort of condensation of information in this sense, and at the same time AI or other machine learning approach, well, machine learning in general, including eventually adaptive parametric or non-parametric modeling, which is also very, very interesting, in order to be able to build a mechanistic understanding of what's happening. Being an engineer, I like to understand how things work, not just what they do. But the point is that I think that will definitely work hand in hand. And we all know that an image is worth more than 1,000 words. Here really is the case of where an image carries the key to unlocking zillions of data in a sense and understanding of information.
Thanks, Danny. And Stefano, based on your non-experience, so you are, the best, point of view.
I'm actually a bit surprised by your point, because I would have thought the reverse. That is, the fact is that for us coming from the clinical, the biological field, our idea is that the application of these methods is much more advanced in other areas, because I mean, diagnosis, what we've been talking about, both myself and Christian, is basically classification and prediction. Only in the medical field, they are called under different names. This diagnosis and prognosis. But the basic problem is the same, of course. The methods need to be very different. But I would say that I share all the views which have been expressed. I'm absolutely optimistic. I'm happy to hear that you think that the diagnostic applications are more advanced, for example, in the case of image analysis, than in other fields. My preconception was that it was the reverse.
My point was like, you have been looking to image, I think way much, before than people that were working with Earth observation. So the imaging field,
you are right.
Yeah. So that was the point. So I'm happy to close with a final opinion of the youngest. So usually the youngest has the best ideas. That's I do think so. Maria Jose and Bruna, the final floor is yours, because youngest has the best idea. So what is your point of view?
Well, I think that I can say that there is this challenge of combining the different types of data sets to then move into the AI world. But I think specifically open data and having access to young scientists to this type of data sets to then explore and create new models and use AI and machine learning is one of the biggest challenges that we have right now.
Thanks, Maria Jose. Bruna, so last but not least.
I don't know much what to say. I think I'm just glad that I could see like such a range of topics all brought together under sort of a same idea. We moved from environmental science and coastal mapping to medicine, and yeah, I don't know much what to say right now.
Okay, so I thanks all the audience that was stable along the 2 hours. So looks like that we were at least interesting. So I'm happy about that. And I thanks the organization, the network organization for the texture. I thanks first of all Anna Chernilla from YUS that was supporting all of us from behind, and it's always complicated. So it's a double thanks. And thanks to all the speakers. It was really interesting, and thanks for availability, because in this complex world of video conference where we all stay in 6 to 7 video conference at the same time, having 2 hours for a discussion, it's always good. So thanks to all, and I hope that you enjoy the discussion.
Thank you.
Bye.
Ciao, grazie.
Bye.
Bye.